Okay, I am Amy Gisora, and welcome to another important session in the ATLT Insight Series. I am thrilled today to open today's session, and I will start off by introducing ATLT. All Things Labs and Testing, that is ATLT for short, is a transformative platform dedicated to driving excellence in laboratory science, accreditation, and quality testing across the continent. Our mission is to unite industry leaders, regulators, innovators, practitioners, and academia, whether virtually or in person, to share best practices, showcase breakthrough technologies, and collectively address the challenges that hold our sectors back. We focus on critical sectors that form the backbone of Africa's sustainable development, including agriculture and food, water and irrigation, environment, engineering, mining and energy, forensics, and ICT. Every one of these sectors depends fundamentally on robust, reliable testing because what gets tested gets trusted. The ATLT Insight Series is crafted under our theme, Growing Africa Through Quality Testing. This initiative connects you directly with leading subject matter experts and thought leaders who are shaping the future of testing in Africa. Our series is anchored on 4 pillars. That is thought leadership, where we share knowledge and foster conversations on best practices, innovation spotlights to highlight emerging technologies and their transformative impact, knowledge exchange, sharing proven solutions and best practices that work, and industry challenges, tackling sector-specific barriers to growth and development. Today's webinar embodies the spirit of innovation driving African laboratories. Dr. Caleb Luvonga is a prolific speaker and consummate analytical chemist with over 20 years of hands-on experience. He has demonstrated expertise in separation science, elemental speciation, and mass spectrometry. He currently serves as the manager of the Organic Laboratory at the Kenya Bureau of Standards, and thus, this presentation promises to illuminate how modern analytical techniques, combined with computational intelligence, can transform complex chemical analysis challenges faced in laboratories today. It is a testament to homegrown expertise and research that will strengthen continent-wide food quality assurance and trade facilitation. The webinar is a 40-minute presentation followed by a 10-minute Q&A session. So you are encouraged to submit your questions anytime via the Meet Q&A tool or chat, which we will address as many as possible. Thus, it is my genuine pleasure to welcome Dr. Caleb Luvonga to the virtual stage. Dr. Caleb Luvonga, the floor is yours. Dr. Luvonga. Apologies, he's currently having some technical difficulties. He had just joined the call. Just give him one moment to join again. As we wait for him to join in, by all means, prepare yourselves with any questions that you might have prior and share the meeting with those with whom you know would like to attend or would gain insightful Insights from his expertise. Dr. Caleb Luvonga, I see that you've been able to join us. When you're ready, you can share your screen.
All right, thank you. Are you able to see my screen? Oh, sorry. Just a minute.
Yes, we can.
Okay.
Thank you.
Thank you. Sorry, there was a power outage, so I lost network, but I'm back. Now, I didn't hear the last bit of what Aime was sharing, but today we are going to be looking at developing a predictive mass spectra database for structural elucidation and identification of novel arsenolipids in seafood. Anyway, let's proceed. So typically, arsenolipids are identified in seafood product and the environmental material using reversed phase separation, using gradient elution and fractionation prior to identification. So the arsenolipids are extracted and they are detected into fractions of the sample extract. So the arsenolipids are separated into fractions according to their polarity and the elution order for those ones who understand a bit of chromatography. And the early eluting arsenolipids are usually species that are more hydrophilic, short chain, such as the fatty acid containing arsenic compounds, and then followed by the medium chain, and then of course you get to the hydrophobics. Now, so in this presentation, I'm just going to be demonstrating the development and utility of a comprehensive arsenolipid structural database in the identification of arsenolipids in seafood. So what is arsenic? When you are talking about arsenic, most of the time people are wondering what is arsenic. So arsenic is an element in the periodic table. It's on a group 5 or group 15, depending on how you read the periodic table. And it is a ubiquitous, toxic, natural occurring element that occurs in the environment in a variety of chemical forms as a result of natural, geological, and historical anthropogenic activities like smelting, mining, and the use of fertilizer. So arsenic is monoisotopic, and it's electron deficient element that has no non-biological role in the human body. It exists in 4 oxidation states, and you can see there the 4 oxidation states of arsenic. So we have the trivalent arsenic, that is with a valency of 3. We have the pentavalent arsenic form, and then we also have the elemental arsenic, and we have arsen or arsine, which is generally a gas. So the chemical form usually determines the bioavailability, mobility, and toxicity. So the general population is usually exposed to arsenic through food, drinking water, air, soil, and dust. So food and drinking water are the most important sources of oral exposure to arsenic. Now, let's look at the toxicity of arsenic. When you look at the arsenic species, the lethal dose for arsenicals in mice or rats, the trivalent arsenic is the lethal dose is 4.5 parts per million. The pentavalent is 14 to 18 parts per million. The mono the MMA and the DMA usually ranges between 1200 and 1800, and then you have arsenobutane, which is mostly considered to be non-toxic. So typically, the lower the number of arsenic is, the oxidation number, the higher the toxicity, and the higher the methylation is, the lower the toxicity. So the absorption of arsenic compounds vary depending on the chemical species, the solubility of each form, and the matrix in which it is present. For example, the trivalent inorganic arsenic is usually present in water, and it's at 100%. It's 100% bioavailable. While in rice, the one that we usually eat, the bioavailability of arsenic is around 90%. So in this particular case, now this becomes important kinds of food or medium for transfer of arsenic into the human system. Now, when you look at the toxicological profile of arsenic, so from a food safety standpoint, and based on the International Agency for Research and Cancer classification, arsenicals in seafood can be grouped into three broad categories, as shown there. So group 1 comprises of inorganic arsenic that are characterized as carcinogens with a lethal dose, as I mentioned, of between 4.5 and 18 milligram per kilogram. Then we have the group B, which consists of the methylated arsenicals with moderate toxicity and high molecular compounds, which mostly have a non-toxicity. And lastly, we have arsenobutane. Arsenobutane is known to be non-toxic. It has a little dose of more than 10,000 milligrams per kilogram. So there's need to establish the toxicological profile for the novel arsenicals, which have been witnessed potential exponential increase since they were first discovered in or characterized in 2008. So arsenic speciation in seafood is challenging. And the reason why it's challenging is because there are many chemical forms and oxidation states of arsenicals, and there's also a lot of interconversion between the species, and there's also complexity of the matrix, for example, the seafood matrix. This one, coupled with the lack of well-characterized and commercially available standards and CRM, makes arsenical the determination of the arsenic profile or arsenic speciation more a little bit challenging. So when you're talking about arsenic species, what are we talking about? We are going to start by looking at inorganic arsenic, and this is usually the major component, it's a minor component in seafood, and it is known to be carcinogenic. And there are two kinds. There's arsenate, which is the pentavalent form of arsenic, and then there's arsenite, which is the trivalent form of arsenic. Now, another group of arsenicals are arsenobutane. I've already mentioned it. That's the chemical structure of arsenobutane. This is the most abundant arsenic species, and it's found in shellfish, finfish, and it's mostly non-toxic. The other one are the methylated arsenic, which are minor constituents of seafood, and they're usually metabolites of the trivalent inorganic arsenic, arsenosugars, and the arsenolipids. So that is the general form in which they appear. So the OH groups or the hydroxyl groups of arsenate or arsenite are usually replaced by alkyl groups to form the methylated arsenicals. The others are arsenosugars, which are the major arsenic compounds that are found in seaweed, and they are usually metabolized by human to form dimethyl arsenate. So that they occur in a number of forms. I've just given an example there of arsenosugar 328, 392, etc. And then you also have arsenic-containing phospholipids. That's the structure arsenic-containing hydrocarbons. This is arsenic, and then it has a hydrocarbon chain. And then there's arsenic-containing phosphatidylcholines. That's the example. And then there's also arsenic-containing fatty acids. So those are the many different forms of arsenic species that exist in nature. So they stand at more than 200 lipophilic arsenicals that are known. That is excluding the arsenosugars. Now, When you look at the toxicity studies of arsenic, so several toxicity studies have been performed on arsenic species that are found in seafood to evaluate their toxicity profile. So arsenic containing hydrocarbons have been found to demonstrate substantial toxicity equivalent to that of the trivalent arsenic species, and also they are able to cross the blood-brain barriers, which makes them very toxic to the human body. Now, when you look at the health effects of the arsenic exposure, in humans, inorganic arsenic is rapidly cleared from the blood and it is widely distributed to almost all organs in the body. That is the liver, the kidney, the heart, the lungs. They are storage reservoirs for arsenic with very little accumulation in the brain and the muscle tissues. So this accumulation is usually associated with various disorders, including skin lesions, diabetes, hepatotoxicity, cancer, developmental toxicity, neurotoxicity, and nephrotoxicity. Now, in view of this, it is important that you are able to identify, you are able to quantify the arsenic species so that we are able to come up with measures or regulatory regimens that will help us to monitor and control the arsenic species. So let me come now to the topic of the day, which is basically the development of an arsenolipid In-Silico library. So this is the setup. What happened is that I went and did literature review. The first step was to perform literature search for structure determination. So the structures of arsenolipids that were reported in the literature were extracted, and also captured the images of the structure description and the elemental formula of the proposed structure. And I used a software called ChemDraw to get to draw the individual structures, and then I converted them into the simplified molecular input line entry system, or SMILES, and international chemical identification, or INCHI format. So there are two formats in which I store the structure, in SMILES format and in INCHI format. So SMILES format is basically a string of letters, mostly carbon, oxygen, but it does not include hydrogen in that structure. So for each arsenolipid structure and the In-Silico fragmentation mass spectrum, it was generated using a software called the competitive fragmentation metabolite identification system, which is an online software. You can easily find it and it's freely available online. So for each compound, 3 different fragmentation mass spectra were predicted at low, that is 10 volts, medium 20 volt, and high 40 volt ionization energy, and were stored as text files in the both positive and negative ionization mode. So the In-Silico spectra were compared with the fragmentation spectra provided in the literature. So basically, what I'm trying to explain is this. So the first step was basically to get the arsenolipid structures extract them from literature, and then I went and did the prediction of the mass spectra of those arsenolipids using the software, that the competitive fragmentation molecular metabolite identification software version 3.0 is freely available online. If you just take that one and you type it, you're going to be able to see the software. So from there, I was able now to get there. I've gotten the molecular structures using as SMILES, and then the other one I've gotten the mass data or the mass spectra using the software. Then I put this together into an In-Silico mass spectra library, and using that mass spectra library, using machine learning, I was able to train the system to recognize the different forms of arsenolipids and be able to identify them. So I was able to use it to predict the structure. So there's the experimental data there's the In-Silico data that was validated experimentally, and then now there's the data that is generated, and then we use the software now to try and establish the molecular structure of the compound. So basically, what happened is that so from the literature review, we were able to reveal 10 classes of arsenolipids based on their structural features, that is the head groups and their side chains. So when you look at the diagram there, you're going to see there's the smiles. So that one basically gives it gives us the structure of the compound, and R is the side chain. So R1 means that there's one side chain which is a hydrocarbon, and then you can also have a reversed fatty acid, you can have a fatty alcohol, you can also have an alcohol or an OH group, etc., depending on the compound that we are looking at. So based on these generic structures that we developed and the side chains, we were able to generate a list of arsenolipids that were categorized in the 10 different classes based on their structural features and the others grouping, and then we were able to establish the generic structures in which the different side chains were to be inserted. So basically this structure, the way it is, this is a generic structure. So the R group is the side chain that needs to be instructed. So the scaffold of the core structure of the different classes of arsenolipids was generated using the ChemDraw software, and it was saved in SMILES format. So the different classes of side chains, that is the alkyl groups, the acyl groups, the terpenoids, the fatty alcohols, were identified, for which a list of possible side chains. We put the possible side chains together, and then now when you put it together, we are able now to get a number of products, or a number of possible compounds, that arsenolipid compounds that we can get. Now, I also wrote an R script using the R programming language. I used it to combine the generic structure from the different arsenolipids classes with their possible side chain to generate a list of predicted arsenolipids that are presented in the SMILES format. So generally, this is how the schema of the relational database. Now, considering that we had the scaffold where we were adding the side chains, it has a head group, and then we are adding in the side chain depending on the compound. There's a possibility of getting so many compounds, an explosion of structures. So to avoid the combination explosion of the number of structures, we applied constraints. For example, we constrained the length of the alkyl carbon chain to be between carbon 4 and carbon 34. The other thing that I did was the double bonds in a single alkyl chain were constrained between 0 and 6, and mostly the main carbon chain that we're looking at was carbon 18. And then we also removed the transconformational structures, which are not commonly found in nature and are not reported in literature. And then this one led us to getting 78 possible alkyl side chains. Using similar rules, we also handled the acyl groups, the terpenoids and fatty alcohols. And in this particular case, we restricted the carbon chain between carbon 4 and carbon 28 for the acyl group, carbon 4 and carbon 20 for terpenoids, and carbon 4 and carbon 30 for the fatty alcohols. And then this gave us 63, 33, and 84 possible side chains. So using this strategy, we were able to reduce the transacyl glycerol arsenic containing transacyl acyl glycerol from getting over 1 million to around 250,000 structures. And then the total of all the predicted structures that was able to generate was 270,000 arsenolipids. So So this figure shows generally this slide are just showing you the schema, and then also the database that was developed, and the database was developed in my SQL server. So looking at now the database itself, after we generated the list of predicted arsenolipid structures. Now I went now to look at each of the structures, the predicted structures. So I did physical curation of the structures, checking each one of them for accuracy to see if they are obeying the octet rules, etc. If the side chains were inserted properly or were inserted in a reverse direction, etc. So it took a lot of time looking at all the more than 270,000 structures of arsenolipids. And then it must be noted that not all the computationally generated structures exist in nature. While there might be a possibility that some of the structures that might be existing in nature may be missed out due to the constraints that I explained earlier on. So some of the structural errors were discovered, and these were mostly related to the double bond configuration of the saturated side chains, because the R programming language does not work well with the forward slashes, and thus it was ignoring them while it was generating the final SMILES format of the predicted structure. So this resulted in the predicted structures generating error messages while I was trying to do the validation using ChemTro. And then I had to go and edit the R script, and the errors were corrected. So the other sources of errors was also related to the orientation of the inserted side chain. So there is need for the to indicate the directionality of the fatty acid, either as a reverse fatty acid or as a normal fatty acid, so that we do not insert the fatty acid in the structure in the wrong orientation that does not exist in nature. Now, the other thing is that the library search is a cross-platform open source software, and the back end of this database, it consists of the MySQL server, as I had already mentioned, and the front end is web-based, and it is developed in Python Flask web framework. So the Spectral library has the web-based graphical user interface, and it enables the search of compounds, or you can either search this database by compound or by an unknown spectrum. So if you look keenly on the image that I've put there, you can see search by compound, or you can see search by spectrum. So those are the two ways in which you are able to search the database. Now let's look at how you are able to search by compound identification. In this particular case, when you say search by compound, it gives you that window, and then you choose the filters to use. So one of the filters that you are able to use is the compound name. You can also use the molecular formula. You can use the CAS number. You can use the SMILES. You can also use the INCHI. Those are some of the filters that you can use to filter the information that you're looking at. So when you're searching by compound ID, so for example, when you're giving the short form of arsenic containing hydrocarbons, it's ASHC. So arsenic containing hydrocarbons, it's usually a combination of the class of the compound, which is ASHC, and the molecular formula or the molecular mass, which is a number. So the molecular mass of maybe arsenic containing hydrocarbon can be 332, 364, 5, etc. So the SMILES formula, or the SMILES notation for the same, is given there. The molecular formula is given there. The class of the compound is given there. And then it also gives the CAS number and the INCHI number. So all this information are available when you're searching by the compound ID. So the compound ID could be arsenic containing hydrocarbon number 332. If you put it there, it will give you exactly that compound. It gives you the mass, the chemical structure, and the INCHI, and all the information about the compound. The beautiful thing about the software is that you can actually insert a half a partial partial information. For example, you can put ASHC, which is arsenic containing hydrocarbons. It will give you a list of all arsenic containing hydrocarbons with their molecular formula. So if you want to narrow it down to a specific arsenic containing hydrocarbon, then you need to give the molecular formula. So the partial searches are possible using this software. So this is an example. Now, when you say arsenic containing hydrocarbon 332, it only picks that specific arsenic containing hydrocarbon, as I explained in the previous slide. Now, you can also do partial search text matching using maybe a part of the name of the compound, like dimethyl asteroid. So if you write just dimethyl asteroid, it will bring a list of all the compounds that have dimethyl asteroid in their name. So in this particular case, if you're just searching and you're not so sure about what you're looking for, you can put a partial, and then it will just go to the database and it's going to list all the compounds that have dimethyl asteroid in their names. Now, you can also search by SMILE. So you go and get the SMILE's notation. If you're using ChemDraw or whatever, once you get the SMILE's notation, once you put in the SMILE's, it will just bring the exact compound that you have inputted using the SMILE's notation. You can also use the CAS number of the compound. If you know the CAS number of the compound, you just input the CAS number, and it's going to bring you the compound and all the information about the compound. It's going to give you the INCHI notation, the SMILE's, the molecular formula, the class of the compound, etc. All that information is available in the database. Now, the other one is that you can also input the molecular formula. You can just go and put whatever molecular formula. Maybe you have done some sort of experimentation and you are able to come up with maybe the molecular mass, and using the chemical tools or techniques, you are able to come up with some form of molecular formula. So you can just try out in the database by inputting the molecular formula, and it's going to give you a compound that closely relates to the molecular formula that you have inputted. Another way is when you search by compound or using INCHI, that is the International Chemical Identification number. So when you put the International Chemical Identification number in the system, it will bring you also the compound that you are looking for. There's another way in which you can actually search by spectral data. So searching by spectral data, there are a number of things that you are going to see. First of all, you either have your own spectra that you have generated in the laboratory experimentally. So once you have that spectra, there is this white space where you're seeing so many numbers. You can just check the spectra. The spectra, by there for information, spectra usually come. The spectra that you usually see that defines the compound usually is represented in terms of numbers, the way you're seeing in that white area. So that spectra is what you're able to generate, and you copy that spectra and you paste on this area of the unknown spectrum, and then you need to set the ionization mode either positive or negative. If you want, you can input the molecular ion resolution. That is if you want, but you can leave that as blank. You can also put the precursor ion. So you can put the molecular mass of precursor ion, and you can also put precursor ion resolution, depending on how you want to filter or how you want to increase the accuracy of your identification. All these features are available in the system, so you are able to do that, and it is now going to give you it's going to give you a table after I've done all that, then you click, you see there's a button there for submit. So once you submit, then you are going to get the compound. It's going to give you a table which shows the compound ID, the compound name, the class, the precursor ion, the match. So it gives you in terms of percentage. So the higher the percentage of the match, the more likely the compound it is. So if you get 100% match, it means that the compound can positively be identified by the system. And then there's also the ionization energy. You can put it and you say that this spectrum is generated at 10 electron volt, 20 electron volt, or 40 electron volt. It gives you the molecular formulas, SMILES, notation, the CAS number if present. Sometimes it's not there, and then also the Inchi notation. So that is how this one can be used. Now, clicking on the compound ID, which is the ones on the left, when you see compound ID, you see they are yellow, they're bluish in color. So those are the active links, and they bring the visual representation of the unknown spectra, and the one found in the database is shown, which is shown in this slide. So, sorry, in this slide. So this is basically what I'm saying. Once you click on that active button, the link, this is the information that it gives. Now it gives you the visual representation of the matching spectra from the library alongside the unknown spectrum for visual comparison of the two spectra. So it is interactive, and it allows you to zoom in. So the butterfly diagram, the one that you see up here, shows the unknown spectrum, how the unknown spectrum compares with the spectra that is available in the database, and you are able to see how closely they agree one to another. Now, apart from that, it also gives you all the other information like the compound ID, the name, class, etc., all the information that you might need for the identification of your compound. So these are just examples of the data that you can get from the system. That's another one. And when you look at it, you'll see the spectra or the visual representation keeps on changing, and the structure down there under the mass spectrum, there's a structure. The structure down there also keeps on changing as you look at the spectrum. Now, there's the other thing about error messages. There are times when you go and you put names of compounds that are not either present or whatever. So it gives you an alert, and it says you that there are no results were found in the database for your query. This is we're just trying to test if the system is able to capture all the information. Now, as I come to the conclusion, I'm just saying that more than we were able to generate more than 270,000 arsenolipid structures, and we were able to predict their spectral data, and we developed a search engine which was in good agreement with the experimental data that was reported in literature. Now, the work that has been presented here, it serves as a proof of concept of the operation and functionality of the arsenolipid search engine. So it just shows that it is actually possible to develop a database for compound identification using in-silico techniques. And if you are able to experimentally generate this data in the laboratory, then you can now use the experimental data generated in the laboratory to validate if your tool is working well. And in our case, the experimental data agreed very well with the data that was generated in silico, and the database that was developed from there. So the tool is also developed or deployed on a web-based platform. So this one enhances the usability and accessibility of the system online. So anybody from anywhere can actually log into the system, and they're able to check, and they're able to see if they can search for the information that they want from the database. So it is not limited by space or time. It is available to anybody anywhere. Now, the other thing is it also provides us with a cheaper means for identification of arsenic-containing compounds using their tandem mass spectra data. So if in the laboratory you are able to generate some data for mass spectra data, then you can just use this tool for the identification of the unknown compound. And the other thing that I'd like to say is that the technique for development, basically what I'm saying here is the tool that we have developed is quite simple. Once you understand what you want to do, the tools are easy to use. ChemDraw, you need to learn a bit of R. R is not so complicated. MySQL is not complicated. So all these tools that I was using are easy, they're simple, and they are readily transferable to any kind of project that is related to what we are talking about. Now, due to the constraint of resources and time, I had envisioned to acquire more experimental mass spectra to further validate and extend the Arsenolipid library. But this was not possible because of constraints of time and resources. And for this reason, secondary data from other sources was necessary. So in this particular case, I did literature review, collected the information that was available there, and then though there was good agreement between the predicted and experimental mass spectral data, they still need to collect data for further validation and extension of the mass spectral library. Ladies and gentlemen, thank you very much. I can now entertain the questions.
Thank you, Dr. Luvonga, especially for being able to put everything all under 40 minutes. It's very impressive. There are a couple of questions, so I believe we can start off just in order. So the first question that came up is asking, what molecular descriptors did you use to develop the machine learning model? From Mr. Eric Kibagendi. I can type out the ones.
Can I take that one first?
Yes.
So the molecular descriptor, basically what I did is, first of all, I got the structure of the compound, and then after you have gotten the structure of the compound, this is now the information that I got from literature. After I got the structure of the compound, then I now took that information and using ChemDraw. ChemDraw can actually take the molecular structure, and then it gives you the SMILES notation and the INCHI notation. So once you have the SMILES notation and the INCHI notation, this is a very powerful tool because it gives you not only the structure, it gives you the conformation of the compound. It also gives you the orientation and everything, the double bonds and how they're oriented, if it's in the cis form, in the trans form, etc. All this information it's generated for you by ChemDraw. So this is a very powerful tool. Now, after I had generated all this information, the SMILES notation, you can easily now copy the SMILES information into the software, the online software, the CFMID software, and then it now easily generates for you the mass spectra. So that is what I used to describe and to identify the compounds that I was working with. So basically, I first of all looked at the class of compounds. So there was the 10 classes of compounds. So after I identified the 10 classes of compounds, then I came up with a scaffold or a framework that can show the head group and the side chains. So once I had that, then it was now easy to now rapidly generate all the other structures that I have shown you in the presentation.
Thank you very much, and I hope that is sufficient for Mr. Eric Kibangedi. We will move on to the next question by Mr. Samuel Ngure, and he posted it on the chat. He has two questions actually. So the first one he has is, how do you factor in for any possible biotransformed products in your annotation tool?
Sorry, come again.
How do you factor in for any possible biotransformed products in your annotation tool.
Okay.
And then his second question is, how do you deal with fragments with small m or z values whose spectra through unique might be masked by unwanted spectral noise?
Okay. I'll start with the last one. So remember that this one is we are, first of all, I have to start by saying that what you're developing, you are developing Spectra using computers. So the computer, you give it the information of a compound, and it gives you the mass spectra that is expected, or that can be predicted from that compound. So once you have generated this information for the from the system, there is no chance for having small compounds with small signals that cannot be detected by the system. Because first of all, remember, I talked about the constraints. We said that the system can only have arsenic containing compounds that have a carbon chain of 4 onwards. So that means that arsenic itself already has a mass to charge ratio of 75. Now, when you take 4 carbons, so you see any mass spectra is able to read such a fragment. So it's not possible for you to lose. For as long as it is attached to arsenic, you are able to see it using the mass spectra. Now, there's also how we are able to factor or deal with the issue of possible biotransformed byproducts. So, in this particular case, most of the time we are looking at you have to give me an input. You are the one who generates the spectra. So once you have generated the spectra, that spectra what we feed into the prediction tool, and then it gives us the possible compounds that can be formed. And by this time, I forgot to mention something. We actually have some compounds. We actually have some compounds, some addants and that were generated by transformation or digestion or whatever. Those compounds we actually generated them and we added them into the database. So if you have compounds that are like positively charged, naturally positively charged, naturally negatively charged, they can also be identified using the tool. I don't know if I've answered that question. If I didn't answer it well, you can always shoot me an email, and I'll endeavor to answer it. I'll endeavor to engage properly and answer the question to your satisfaction.
From Mr. Samuel's response, I believe you have answered it sufficiently. So okay. There are a couple of other questions. So there's one, sadly has been posted anonymously, but they're asking, how do you see the Arsenolipids database being integrated into regulatory monitoring and inter-laboratory programs? And if there are plans for community curation, version control, and linking entries to reference standards or proficiency schemes to support enforcement and traceability.
All right. Wow, that's a mouthful. Anyway.
Yes.
Ideally, the reason why we're doing all this is to, first of all, remember, most of the time when we are doing analysis of arsenic in whatever compounds, if it's in cosmetic products, if it's in food, if it's in environmental material, etc., we usually measure total arsenic. And that is nonsense. Well, sorry for using that term. But yeah, it does not make any sense to try to do total arsenic, because not all forms of arsenic are poisonous or toxic, as I showed you. The only toxic form is the inorganic arsenic, actually the trivalent inorganic arsenic. So you're supposed to be able to get the total arsenic, and then you do speciation to get the different species that are present in that arsenic, in the total arsenic, and then quantify the species to know what proportion constitutes the carcinogenic arsenic and what proportion constitutes the non-toxic arsenic. Now, let me surprise you. In fish, which is, or the seafood, most of the time, the vast majority of arsenic in seafood is arsenobutane, which is non-toxic. Actually, more than 95% of arsenic in seafood is in the form of arsenobutane, which is non-toxic. So if you go and then you do total arsenic and then you say that the total arsenic is so much and then there are MRLs, then you might actually be condemning something that does not have any deleterious effect or hazardous effect to the human system. Arsenobutane, when you take it through food, it actually comes out through urine without being altered in any way. So that is non-toxic to the human body. Now, coming to regulatory practices, we have to first of all generate the data. So once you have the data, it will inform the regulatory practice, because you cannot regulate what you do not know. You need to generate the data, and then the data needs to be evaluated. Then the toxicity studies need to be done, and then identify the fractions that are toxic, and then we also identify the levels present in food, and then we can be able to say that the food is safe or it is not safe for regulatory purposes. Now, so we need to generate a lot of data, and part of the reason why I'm doing this is just to try and create an interest in for upcoming researchers and the people who are in academia to venture into this area, because there's a lot of work to be done in this area and not a lot of information that can be used for regulatory purposes. Now, for you to be able to identify the different species of arsenic, you need very high, very expensive equipment, and you also need high level, you need to know a lot of organic chemistry, organic synthesis, etc., NMR, nuclear magnetic resonance, etc. That is why I was trying to come up with an easy way of identifying these compounds using a database that you can actually easily extract information and then put it in what is it called? In an equipment, in an MS, and then it gives you spectra, collect the spectra, put it in the database, and then it's hopefully your compound is able to be identified using the database that would have developed. So that is basically what I was hoping to do. Now, talking about proficiency testing, talking about reference material, etc. This project, as I was doing it, actually it was brought, it came up because of a need for reference materials. And as I was doing this project, part of the work was to develop a reference material, and we developed a reference material. It's called for the National Institute for Standards and Technology, NIST. That is SRM, I think 2390, whatever, for GUIDAC, for identification of inorganic arsenic and also total arsenic. And so that was just part of the effort, but there's a lot more, especially when you look at the Kenyan context. There's a lot of work to be done in this area. Because remember, we are we have the Rift Valley, and then you have the hot springs and geysers, etc. All these ones usually generate arsenic. There's a lot of lumbering and whatever. All these anthropogenic activities also generate arsenic. Who tests for the arsenic? How are we testing for it? Are we testing for the species of arsenic, or are we doing total arsenic? Those are the questions that I'm posing to you, ladies and gentlemen.
Thank you so much, Dr. So there's just one more question. I think we can try and squeeze it in. And it's by Mr. Josephat Abuga. And he's asking, will the MS be able to identify the different forms of arsenolipids? And if yes, which criteria will you use to separate them?
Right. The MS is able to identify them. That one I've already demonstrated and proved in the presentation. The criteria that you use to separate them is using first of all, their classes, in which class it belongs, and then the molecular formula. I explained that in one of the slides. So the information that I've inputted there is usually is basically the class of the compounds, maybe arsenic containing hydrocarbon, arsenic containing fatty acid, etc. And then it has a molecular formula to it. So it could be arsenic containing hydrocarbon 332. So using that, the class of the compound and the molecular formula, I'm able to easily separate and identify the different classes of compounds. Because remember, you can have arsenic containing hydrocarbon and also have arsenic containing maybe fatty acid of the same molecular weight, but they are in different classes. So in that particular case, I'm able to separate them. I can say one is a hydrocarbon and another one is a fatty acid. I hope that one answers that.
There are more questions filtering in. Yes, it does answer that completely.
Yeah.
I will state that for those with whom might have joined later or might have missed something, the recording will be up. And as the doctor has shared, he will open his emails, his contacts are right here on the screen. Just in case you have anything, you can even now get it directly from the source through a one-on-one or whatever type of agreements that you have with him. And because of time, I think we will have to close off. So I will, because there are 2 minutes towards the time, I don't think we can take on another question. So firstly, on behalf of everyone, I want to thank you, Dr. Luvonga, for availing yourself and sharing your expertise to the masses, for it has truly been insightful. You have truly worked hard to showcase what is happening within the field. And I truly believe that this will help spark conversations and more research and work as we move forward to not only grow Kenya, but Africa at large. And then to the attendees, we truly, truly appreciate your participation and engagement. And we hope that you find this session both insightful and practical as we work towards transforming food safety and contaminant detection in seafood. So I will start off by saying thank you all for coming. Thank you, Dr. Luvonga. And I hope you all have a lovely, lovely day. And we look forward to seeing you at our next ATLT Insight Series webinar. I don't know if Doctor, if you have anything to say before we close off officially.
Thank you, Aime, for this opportunity. I would like to thank all the participants for joining in, for your interest in what we've done. I've been able to present. This was part of my PhD work. And the reason why I actually did that, this is partly because of COVID, so I was not able to have access to the laboratory, but I still needed to finish my work, so I had to come up with a creative way of finishing up my work. Now, I also want to thank Aime and the ATLT team for giving me this platform to share the knowledge. I want to thank my employer, Kenya Bureau of Standards, for allowing me time to go and study, and even to share this information. The management of KEBS are aware that this one is happening. So I'd like to really thank them. And I would just want to say that if anybody has a question or whatever, I've shared my email address and then my telephone number. You can reach me at any particular time. I am open to a conversation, a discussion with you. And I'm hoping that everything will be fine. Thank you very much, and hope to hear from you soon. Thank you.
Thank you. We deeply appreciate your participation and engagement, and we encourage all of you to continue the conversation. Thank you all for availing yourselves and have a lovely day. We will see you in the next ATLT Insight Series webinar. Goodbye.
Thanks and goodbye.
Goodbye.